Hey team, this is your chemist coach coming at you for video number 6 in our acid base sequence. For my class, this is chapter 16, second semester general chemistry. So what we're going to look at now is take all of these concepts that we've learned, Kas, Kbs, pH scales, all that fun stuff, and ultimately we're going to be looking at different acid and base solutions, whether they're strong or weak, and going, well, what's the pH? That's pretty much the ultimate question, as well as what are the concentrations of any particular species we're after. Usually we're after the principal species, not minor species, but principal species. Let's focus on strong species first, strong acids and bases, and those I think are easier because we can make some simplifying assumptions and avoid ice tables. And then we'll look at weak acids and weak bases where we're forced to use ice tables because of the equilibrium, because we don't know how much they ionize. Remember, for strong species, we're assuming 100% ionization. So let's take a look at this board. It's a pretty busy board, but it kind of summarizes everything we're going to be doing. And then we'll do one example problem, maybe two, and we'll see how it works out. So strong acid, strong base solutions. We are going to make the assumption that they are 100% ionizing or dissociating in water. Very large Ka values for strong acids and very large Kb values. So we're assuming it's all products, no reactants in that scenario. But we're also going to make another simplifying assumption. That will always work for my class. Now, depending if you move on to higher levels, you may have to account for this, which really makes it more challenging. But if I have an acidic solution, a strong acid, it's producing hydronium ion, right? But this is a solution, which means that acid is dissolved in water. That means water is also a source of hydronium because of the autoionization of water. Oh, crud! We have two sources of hydronium ion for strong acids, the autoionization of water and the strong acid itself. If I have a strong base, it's also in solution. So I have two sources of hydroxide, the strong base and the autoionization of water. What are we going to do? We're going to ignore any contribution of the hydronium ion or hydroxide ion from the autoionization of water. Because remember, roughly room temperature goes about 10 to the minus 7th molar. Strong acids and strong bases are going to have usually much larger concentrations than that. So we can safely ignore. If I take, for example, here's the autoionization of water. You can see how that produces hydronium ion and hydroxide ion. If I have a strong acid, that strong acid will ionize in water to 100% extent, producing hydronium and the conjugate base of the acid. So we're going to see that the concentration of the hydronium is the same as the original concentration of the acid, and the concentration of the conjugate base is the same concentration as the original acid. So that strong acid will have hydronium ions from the strong acid and from the water, but we can ignore the water. So if we took the hydronium ion concentration from the strong acid and added the hydronium ion concentration from the water, it would still equal the contribution from the strong acid. It's like adding, 200 plus 0.002 or something. That's still pretty much just 200. You go to the Pacific Ocean and take a spoonful of water out of it. I have decreased the volume of the Pacific Ocean. Yeah, technically, but the Pacific Ocean didn't notice. All right, so you can take the hydronium from the acid and add that from the water, and the strong acid went, okay, didn't notice. I got $8 million and you gave me 2 cents. Whoop-de-doody. All right, so that's going to really make our math easier. Hopefully you're okay with those assumptions. Same thing if I have a strong base. Usually it's going to be an alkali metal hydroxide like sodium hydroxide, potassium hydroxide, something like that. That's going to dissociate, because it's an ionic species, 100% in water. And so the concentration of the cation and the concentration of the hydroxide ion will be the same as the original base, which makes it easier. That's why we don't need ice tables. And then you've got the OH minus contribution from the strong base and the OH minus from the contribution of the autoionization of water. But we're going to make the same assumption that the hydroxide ion concentration from the strong base is so huge. How huge is it? It's so huge we can ignore the OH minus from the water. All right. So I'm not going to do all this again. We're always going to have that underlying background assumption that we're ignoring the autoionization of water as far as contributing H3O plus or OH minus. So let's do an actual strong acid problem and a strong base problem, see how easy these really are. All right, here's a typical type of problem you'll see on a quiz or an exam, where we have, and you got to recognize, you got to know what those strong acids are. Now, you can also use your acid-base table, and you'll see on the acid-base table anything above the hydronium ion there counts as a strong acid. So HI, HBr, HCl, HClO4, H2SO4, and HNO3. Remember those. So what I'm looking at here, I've got a perchloric acid solution. That's a strong acid. Has a concentration of 4.21 times 10 to the minus fifth molar. I want to know, I'm asked for the concentrations of all of the predominant or major species, which in this case will be the products because it's a strong acid. And what's the pH? So let's calculate those pieces of information. Remember, we're ignoring any hydronium ion contribution from the autoionization of water. That's the last time I'm going to write that. I'm just going to mention it from now on. So let's write the ionization of that strong acid in water. So we've got the perchloric acid donating its H plus to water. 100%, remember we're making two assumptions, 100% ionization of the strong acid in water and no contribution, negligible contribution from water, so we can ignore it. So we're producing hydronium ion and the perchlorate ion, which is the conjugate base over here. If this is 100% ionization, then the concentration of the hydronium ion should equal the concentration of the perchlorate ion, right? Because it's a 1-to-1 mole ratio. Since this is 100%, those should equal the original concentration of the perchloric acid that we started with. That's why these are easy. You don't have to calculate anything. So let's just write that number down. So that'll be 4.21 times 10 to the minus fifth molar. Man, isn't that a piece of cake? Now, we could calculate the OH minus concentration if we wanted to using the KW, but that's not a predominant or major species, so I didn't ask for that. But I could have. All right. We have now successfully, you can think of this as a part A, part B on a test. Part A, what's the concentrations of all major species? Part B, what's the pH? Well, I know the hydronium ion concentration, so I just take the negative log of that and I got the pH. Rock on, baby, let's do it. So pH is negative log of the hydronium ion concentration. So let's take the negative base 10 log of our 4.21 times 10 to the minus 5. Remember, when you take a logarithm, the number of significant digits in the logarithm term in the concentration is the number of decimal places in our answer. We're going to get 3 decimal places. So we're going to do a non-rounded value or intermediate value. Use that vertical dashed line to track the uncertainty and then round that baby appropriately. All right, what did I get when I did this? I got 4.375. 4.375. 3 significant figures gives me 3 decimal places. I'm going to put my vertical dash line there, and I get a 7.1 after that. Remember, pH has no units in that scenario. So this is going to round up because this is greater than 5. So this would be 4.376. Now, you could have anticipated this because we know this is an acid, right? It's a low concentration of an acid, but it's an acid nonetheless, which means its pH should be less than 7. And that's less than 7, right? If that had been a 12 or 13, that would not have made any sense, would it? So you can kind of check your answer. Let's do one with a strong base, and we'll end this video on strong species, and then we'll do weak species. Yay! All right. See if you guys can do this problem on your own, right? So pause the video right now, write this down on a piece of paper, and see what you get, right? So we've got here a solution of sodium hydroxide, which you should recognize as a strong base. We're going to count in this class all solutions of alkali metal hydroxides as strong bases, okay? So we've got a 3.9 times 10 to the minus 2 molar solution of sodium hydroxide. Back in the old day, they called that lye. What's the pH of this one? So it's a simple one thing I'm asking for. Our plan of attack is we're going to take that concentration and we're going to solve for that. Now, there's 2 ways you could do this, right? We could take the hydroxide ion concentration, solve for hydronium ion concentration, and then take the pH. Or remember that little square with the pH square. Or what I'm going to do is take that OH minus ion concentration, calculate the pOH, and then from that I can calculate the pH. So 2 ways you can solve this. But we're going to make that 2 assumptions, right? 100% ionization, or in this case, because it's an ionic compound, a strong base, 100% dissociation in water. And we're going to ignore any contribution of OH minus from the autoionization of water. So let's write our equation up here. So the NaOH, or sodium hydroxide, is going to ionize 100% extent to give us the sodium ion and the hydroxide ion. Since that's 100%, then the concentration of the sodium ion and the hydroxide ion must equal the original concentration of the sodium hydroxide. So, and you can pretty much do this in your head, but I'm going to write it down in case you're reviewing this. So the OH minus ion concentration should be 3.9 times 10 to the minus 2 molar. And if I'd asked for the sodium, you would put that number as well, 3.9 times 10 to the minus 2 molar. You love strong species, very easy to do. It's the weak ones with the reversible arrows that we're going to need ice tables for. All right, I'm going to go ahead and take the negative log of that to get the POH. Right? So POH is the negative log of the hydroxide ion concentration. I cannot go directly to the pH from this because that would put me across a diagonal on that pH square. I got to go over and down or over and up. Those are my only two options. All right, let's plug in our value. Let's take the negative log of 3.9 times 10 to the minus 2. All right. So it's going to be, somewhere between 1 and 3 in that. So what did I get when I did this? I got 1.4089. 1.4089. So think about your uncertainty. I'm taking the logarithm of something, so the number of significant digits in my concentration, which is 2, will be the number of decimal places in my POH. So that's why I have 2 decimal places. Now, I'm not going to round that. I didn't ask for the POH, so I'm not going to round that number. I only round what I specifically asked for. But I'm not done. A lot of students make this mistake and go, there's my answer. Oh, no, it's not. That's the POH. I asked for the pH because everybody thinks in terms of pH. Almost nobody thinks in terms of POH. It's all backwards in our heads, right? So let's finish this problem. We know that the pH plus the POH is 14.00. That would provide it for you. Therefore, the pH is 14.00 minus the POH. So I'm going to subtract that from 14. It's a two-step process, right? So let's take 14.00 minus 1.4089. I'm doing a subtraction, so I'm limited by the largest absolute uncertainty, aka fewest number of decimal places. Got 2 and 2, so I'm going to get 2 decimal places in my answer. Now try to anticipate what you should get. This is a strong base, so we should have a pH higher than 7, closer up the ladder, more towards the, probably 12, 13, 14 range, somewhere in there. It's a strong base. A little higher concentration than we had in our strong acid in the other problem. So I got a 12.59 vertical dash line 1, so it's closer to 12.59 than 12.60. So that will stay at 12.59. And does that make sense to us? Yeah, that's a number bigger than 7, closer up. So the higher that pH, the higher the concentration and the stronger that particular base is. So there's 2 things that really impact the pH of something is the strength of that acid or base and the concentration of that acid or base. Those are the 2 factors. So if I have a stronger base with a higher concentration, I'm going to have a higher pH value. If I have a stronger acid with a higher concentration, it's going to be a lower pH. That's it for strong acids, strong bases. Practice your homework. Let's do the next video with weak acids and bases. Oh no, we're going to need ice tables.